Morning, friends. Welcome to Mind Campus Education Based YouTube channel. And today we are going to see EE3302 Digital Logic Circuits Unit 1 Number Systems and DLL, different types of logical families we are going to see. Okay. So in that I have consolidated the different type of problems that may be asked in the university examination. Okay. One example, let us see: design a binary to gray code conversion circuit. So we have to design a circuit that will convert a binary to another form. So this is code conversion. So we have so many code conversions: binary to gray, binary to hexadecimal, binary to octal. So many conversions are there. So each category have its base. Okay, binary means by means 2. So it is having base value 2. Base value 2 means you have to start with from 0 and 1 are the two base values. If it is quadra means base value is 4, then your number should start from 0 1 2 3. So it will have 4 values. Octal means 8. So binary to octal means 8. Octal, then in that case 0 1 2 3 4 5 6 7 up to 0 to 7 there will be 8 values. This is the concept. If it is hexadecimal means it will be going from 0 to 15, because including 0 we have 16 values. So let's proceed with the binary to gray code conversion. This is the truth table for the binary to gray. Normal binary, we know it is very well 8421 code. You are very familiar with that. It is a 8421 code. So we will proceed for 0 0, and we keep on adding 1 to the previous bits. So if we add 0 with 1, we will be getting 1. If we add 1 normal addition, it will become 2, but in binary we have ones and zeros only, so the next data will be 1 0. If you add one more 1, it will be 1 1. If we add 11 with 1 to the 11, we will be getting 100 plus 1, 101. So like that we have to frame this table. So left hand side I have mentioned it: 0 1 2 3 5 4 5 6. This is the normal decimal number system, and this is the binary code value. This is based on the concept of 8421. So this binary code is also known as 8421 code for a 4-bit number. Otherwise 168421 code for a 5-bit number. Okay. So with the 4 bits we can have to the maximum of 2 power 4 equal to 16 data values. So starting from 0 to 15 there are 16 datas. So how to frame the gray code? Just you have to copy the MSB. So in binary the higher position is 8. So this is MSB, this is LSB. So MSB has to be copied as it is, and the bit next to the MSB, next left to the MSB, it has to be got through the combination of XOR combination of these two bits. So that will be the Z2. So I have at the left hand side I have given the equations. G2 is B3 XOR B2 and B3 XOR B2. You may be clear: B3 XOR B2, and G1 is B2 XOR B1, and G0 is B1 XOR B0. G3 is simply gray code 3 is values are just copied from the B3 values. You can see the same values here and here. So if it is difficult to for you, then you can follow the K map. Okay, in the K map we are very familiar. This is the four variable K map. So we will write the positions, bit positions: 0 1 3 2. It has to be 3 2, 4 5 7 6, and 8 we will be writing at the bottom: 8 9 11 10 12 13 15 14. So if you refer it, you will be having the same: 0 1 3 2 4. We have to proceed here from the 4 4 5 7 6, and next 8 is will be the last: 8 9 11 10, then 12 13 14, 15 14. So from the gray code you have to reference the code. So corresponding for 0, all must be 0 1 00001. So if you follow the equations also, you can get XR means for XR gate output will be 1 for different inputs. It will be XR output will be 0 for same inputs. If both inputs are same, either 0 or 1, it will be output will be okay. Now we have now we have marked the ones for the G2 wherever the G2 comes. So wherever positions the G2 comes, G2 has 1 at 6 7 5 4 5 7 6 and 12 13 14 15. So I have marked here 4 5 6 7 4 5 6 7 12 13 14 15. So now we have two rows with. So if it is two row means if any particular row is completed, you can notice here. If any column is completed, you can notice to the top. If it is covering like this means you have to look both rows and columns. I will show you now in the next problems and all how it comes. Now it is, and the complete row is filled. Okay, this row and this row is completely covered. So corresponding to the row there is 0 1 and 1 0. This is what B3 bar. So if it is 0, then we have to tell it as B3 bar, and if it is 1, we have to tell it as B2. So this is B3 bar B2, and this is B2 B3 bar. So this is the combination of XR combination of B3 and B2. So we have find out the equation. Same way we have to proceed. So this is the final circuit. G3 B3 is same as G3. G3 B3 bit and B2 bit has to be XORed to find G2, and B3 bit, B2 bit and B1 bit has to be XORed to find G1. B1 bit and B0 bit has to be XORed to find G0. So this is the simple example how we have to design how we have to proceed a problem. So if anyone has asked any code to any code conversion, we have to write the truth table. Next we have to draw the K map. We have to simplify the equations. We have to find the logic gates that has to be used. Not only logic in XOR gate needed, you can also use AND gates and OR gates. You have two multiplications and one addition. So in this way also you can proceed. So that is up to you. So next question, I am solving all the repeated university questions only here. Given a frame with bit sequence 110110, this is the sequence and it is being received at this. So determine the method of detecting the error. You just understand the question. They are asking only the method to detect the error. Okay, I have written below the received sequence and the transmitted sequence. There is a yet error in the last bit, but we are able to, since it has been provided, we are able to find there is an error in the last question. But how it has to be detected? We can have error correction codes. If we want to detect and correct the error means, we can go with Hamming code. For detection alone, parity bits alone is enough. So if we follow parity means the extra bit that has to be added to the original data, so that the number of ones is either 1 or odd or even. So if we follow odd parity means it should be the number of ones, counting the number of ones should be odd, and if it is even parity means the number of parity bits should be even. Okay, together with the additional parity bit. Suppose we assume odd parity means, and then the number of transmitter wants to be odd. So considering this, for the transmission data, and the number of bits is 0 7. So since odd parity is maintained, we are not adding any additional bit. The additional bit is 0. So if we made the error means the number of ones becomes 6. So it indicates the odd parity is not satisfied. Hence the occurrence of error is being detected by the odd parity technique. We can also use even parity. We can also use Hamming code, but Hamming code is little bit tedious. So we can go only for the correction of error for Hamming code. Okay, next it is for the correction. A 12-bit Hamming code, a 12-bit Hamming code combining contains 8-bit message and 4 bits of parity. If the words are, understand the question, it is a 12-bit Hamming code. In that, 8-bit is message bits and 4 bits is parity bits. So we have to find which are the message bits, which are the parity bits. If the code words are, if the words are, the total word is, these are the words. We have to segregate, separate the message. And so the structure of the Hamming code is this. So here we have total 12 bits, right? So 0, I am writing here, not I am not writing from 0 to 11, I am writing from 1 to 12. So the parity bits will occupy the positions R naught, R1, that is 2 power 0, 2 power 1, and 2 power 2, 2 power 3, like that it goes on. 2 power 0 is 1, so it is occupying the first position. Okay, this R1 will be occupying the 2 power 1, that means second position. At next bit, 2 power 2 is 4, so the bit number 4 is reserved for parity bit. At next is 2 power 3 is 8, so the bit number 8 is reserved for parity. Next 2 power 4 is 16. Now we have only up to 12, so we need not consider about 2 power 4, that is R power R suffix 4. Sorry, R suffix 4. Yes, it is. Okay, so this is the structure. We write the data from the LSB. So from the previous question, it has been given here. So we will write 1101, 1011, 1001, 0100. So we have to write from the LSB 100, 1001, 1011. So now we can easily find out which are the message bits. So the parity bits location I have told you, it must be the 2 power 0, 2 power 1, 2 power 2, 2 power 3 locations. So remaining bits positions we can understand. Okay, so this is the message bit and parity bit for the first given problem. Second, for the same, in the same way, we are marking the parity bits location, that is 1, 2, 4, 8 position and 16 position. 16 position not available here, so remaining, in this way we have to proceed. So next problem is perform subtraction using 2's complement. So this is one data, this is one other data, we have to subtract these two. So if we are to have to form 2's complement, means we have to take for a subtraction we have to take the 2's complement of the bottom number, that is sub in if it is given when word means a, subtract a from b, then b minus a is the answer. Subtract a, b from a means b minus a minus b is your answer. Okay, keep that in mind. Which is the numerator, which is the denominator, top portion, which one is the larger number, which one is a smaller number, you decide it based upon your words. So subtract a from b means we have to subtract a from the value of b, so b minus a. Subtract b from a means we have to subtract b from the value of a, so keep that in mind. So we will call that to be subtrahend and minuend. Okay, minuend. So we have to take the 2's complement. I have told you how to take the 2's complement. So before taking 2's complement, you count the number of bits. In the second data 110 100, here it is only 4 bits, here it is 6 bits, so I have included 2 additional bits. So this is the number. Okay, so for that number I have taken, this is actually wrong. This is your top data, and for the bottom data I have taken the 2's complement, sorry, 1's complement. That means so this is right, this is 1's complement. So wherever one zeros comes, you have to replace with 1. Wherever 1 come, you have to replace with 0. So this is 1's complement. For adding for 2's complement, you have to add 1 to the 1's complement. Adding 1, you will be getting this data. Okay, 110, 110, 110, 110 you will be getting. So you add to this. If excess carry means you have to neglect this carry. Mm, if excess carry means you have to neglect this carry. That's it. Okay. If carry no comes means your answer is negative. This is the concept. Similarly, in the same way here also they have proceeded. So this is the number, this is the number. So just you can take the 2's complement. So 1 for 1 it is 0 is the complement. So this is 0's complement. Adding 1 we can get the 2's complement. So this will be your answer. I hope you will be very clear with the subtraction. So now reduction, expression reduction. F equal to A bar C, A bar B, A B bar C plus BC. So this for easier identification I have put zeros and ones. So A bar means it is 0, B it is 1, B is not there in this first term. B is not there, so I have included B and B bar. Okay, so this is 0 1. So in between 0 0 0 1 and 0 1 1, so I have included for these two terms. Okay, here C is missing, so this is 0 1. I will be having 0 1 0 0 1 1. So this 0 1 1 0 0 1, these three elements are there. This is having three elements, this is having only two elements, this is 1 1. So 0 1 1 1 1 1. So totally this will be having 2, this will be having 2, this will be having 1. So 5 5 plus 2 7 elements will be there. So if any repetitions is there, we can neglect it. 0 1 1, 3 is here, 3 is here, so I have removed it. And 0 0 1, this is also 0 1 1, so I have removed it. So 3 ones have been removed. So without repetition you have to write the numbers alone. So this is the shortest expression, minimal SOP expression, minimal SOP expression. If they ask write the minimal SOP expression for this, you have to write in this way. Okay, so again ulta, number is given, you have to write the number. This is in terms of, this is called as canonical form actually, sorry, this is termed as numbers, we call it as canonical form, and this is expression form. So canonical numbers are given, you have to frame the for this you can write the canonical form. F equal to summation of what are the numbers we have, starting from 0, increment order you can have it. 0 is not there, 1 is there, this is 1, this is 2, this is 3. So 1 2 3, next is 5 7, 6 is not there. Okay, so this is the way how you have to proceed. The same way here also. So minimal sum of the product expression, A bar C plus A bar B, A B bar C plus BC, like that. Okay, so here also 1 means you can write 0 0 1, right? So you can write in that way, and then you can simplify the equations. So this will be A bar B bar C. 2 means 0 1 0. So which is being which can be replaced? The same here you can get is A bar. So you can have the K map and have the easiest reduction like straight away. So next is Quine-McCluskey method. This is a little bit tedious method, I have to explain to you so many times. So first you have to frame the table 0. For that you have to count, you have to frame group, min terms and status. Group is the first zeroth group is Number of minterms having zeros, fully zeros, 1 zeros, 2 zeros, 3 zeros, 4 zeros, and 5 zeros, and so on. Sorry, not counting the zeros, it is counting the ones, number of ones. No one is there means it belongs to zeroth group. Only one is there means it belongs to one group. Two ones means it belongs to two group. Three ones means three group, and four one means fourth group. So you have to choose. You have to write the elements inside here only if it is available in the question. Otherwise, you need not write. So m naught is not having any zero. So it is any ones. It is not having any one. So it will come under zero group. One is having only one. 8 is having only one. So it comes under one group. 3 is having two ones, and 9 is having two ones. So it is coming under second group. 7 is having three ones. 11 is having three ones. So it comes under third group. 15 is having four ones. So it comes under fourth group. So I hope everyone is clear with the table 0. Table 1, in the same way we have to match it. Now we have to find the matched pair. Matched pair in the sense we have to combine. We have to combine. I will show you how to find the matched pairs and all. You have to, from the table 0, you have to take the elements. Okay, you have to m0 means 40, m1 means 0001. So if there is only single bit change, this is alone changing, single bit change, then it is a matched pair. So you have to combine all the terms, m0 with m1, m0 with m8. So this will be your group number 1 for there. And for the second one, you have to combine with m1 with m3, m1 with m9, and m8 with m3, m8 with m9. Similarly, for the next row, m3 with m7, m3 with m11, m9 with m7, m9 with m11. Similarly, m7 with m15, m11 with m15. So I have framed it. If it is only a matched pair, that means single bit change. If there is only single bit change, I will write the pair, and I will write if there is a match. You listen here. Here there is a match. Okay, 0 is matched. So I have written 0. This is also 0 is matched, written 0. This is also 0 is matched. This alone have the difference. Wherever the difference comes, you put a dash. This is the one I have written here. This is the one I have written here. So this is table number 1. So table number 2 is, now we have to take this as a pair. You have to pair, you have to find the matched pair with this. This is a single element, this is a single element. So m0 m1, m1 m3. So that is not a matched pair, because this is having dash at the end, this is having dash at the second position from the last. So this will not be a matched pair. So this, if we check m0 m1 with m1 m9, it is also not a matched pair. So stay for a second.